Okay. Okay, this is the second part of a review for your statistics test on Chapter 10 on inferencing, and let's go ahead and the first part was just a generalization, and let's do a couple of examples here to wrap it up here. So the mean yield of corn in the U.S. is about 120 bushels per acre. A survey of 20 farmers this year gives a sample mean of 123.8 bushels per acre. We want to know whether this is good evidence that the national mean this year is not 120 bushels per acre. Okay, that part right here is not means it means not equal to. So your null or your alternative hypothesis is going to be it's not equal to. Okay, so if the standard deviation in this population is 10, test your hypotheses at the 5% level. Okay, so let's go ahead and identify the inference toolbox here. So step one, identify the population and the parameter of interest. State your null and alternative hypotheses. Okay, so my population is bushels of corn per acre in the United States, and the parameter of interest is the mean yield per acre. Okay, and so my null hypotheses, H sub O, is equals 120, and my alternative, remember, it doesn't equal. If it said less than, then it would be less than. If it said more than, or raises, or something that reference to that, then you'd do that. But this one right here says is not. So this is going to be a two-tailed test. I'll show you more on that in just a second. So step two, identify the statistical procedure that you're going to use, and then state and verify the conditions required for using this procedure. Okay, so far all we know how to do is the z-test, the one sample z-test. But in the next chapter we're going to do the t-test, you guys. And it depends on if you know the standard deviation or not. Well, since we know the standard deviation is 10, and it's pretty unrealistic. Most of the time we won't know that. But now, since we do, then we use a one sample z-test. Okay. And since n equals 20, we need to know that the population is normally distributed. Well, I don't see anything about a normal population right there, so there's really no way to check this unless they told us that. And so we're not told how the farmers were chosen, so we don't even know if it's a simple random sample of the population that we're doing stuff. So if it's not a SRS, then we may be unable to generalize our results. And also, since n equals 20, the central limit theorem does not ensure the sample is going to be normal. So keep doing your calculations, but you just say something like, I'm going to go ahead and proceed with some caution there, because it just might not be normal. Okay, so step three, calculate the test statistics and the p-value. Illustrate this using a graph. Okay, so there's my my formula, my z-score formula. So I'm going to plug everything in, you guys. So 123 minus 120. And the sample size is 10. I'm sorry, the standard deviation is 10, the sample size is 20 right there. And then so I do this part first, you guys, and so I get that, and then that's pretty easy to see right there. I get that. All right, and when I divide that, I get a z-score of negative 1.7, you guys. So let's see. So there's my chart right there. It's a two-tail, so it's negative 1.7. I'm sorry, it's positive 1.7 and negative 1.7 because it said not equal to. All right, so I got to consider both tails on that right there for my z-score. All right, so now since my z-score always gives me to the left, I'm going to look up negative 1.7. So negative 1.7, when I look that up, I get 0.0446. So that means that that side is also 0.0446. So my p-value is going to be twice that. So I get 0.0892. All right, so there, we've done that. Now step four is to state your conclusion in clear, complete sentences. Okay, so if the true mean is 120 bushels, then there's 8.92% chance of obtaining a random sample whose mean bushel count is not 120. Okay, although that's a low number, it's not sufficient evidence, at least at the 5% level. It's not sufficient evidence to reject your null hypotheses that the mean bushel count is 120. Okay, so it doesn't mean that I absolutely accept them. It just means that I don't have sufficient enough evidence at the 5% level to reject them. Okay. All right, here's try another one. Sulfur compounds cause off odors in wine. So the winemakers want to know the odor thresholds, the lowest concentration of compound that the human nose can detect. The odor thresholds for dimethyl sulfide, DMS, is in trained wine tasters is about 25 micrograms per liter of wine. The untrained noses, me, of the consumers may be less sensitive, however. Here are the DMS odor thresholds for 10 untrained students. So this, remember, this is in college, you guys. So this is a college AP book. So if you're my high school student, you're wondering, well, students drinking wine or smelling wine. No, this is college. So okay, so let's just get over that part. So assume that the standard deviation of the odor thresholds for the untrained noses is 7 milliliters. I'm sorry, what is that? That should be milligrams, mg, milligrams per liter. Okay, that should be an mg right there. Make a stem plot to verify the distribution is roughly symmetrical with no outliers. Give a 95% confidence interval, and then use that. And then, so are we going to be convinced that the mean odor threshold for students is higher than the published threshold of 25? And that again should be milligrams per liter right there. Alrighty, so here we go. So we're going to make a stem plot to verify this. So I did my 20s, 30s, and 40s right there. Okay, so this stem plot is roughly symmetrical, you guys. I don't see any clear outliers right there. So there's a stem plot right there. So they didn't tell me it was normal, so that would be our next step. We'll do more of this in our next chapter with the t-test. We're going to do stem plots a lot, so I just wanted to refresh us how to do stem plots again, you guys. All right, so this one is this plot's reasonably symmetrical with even with a small sample right there. Okay, so I can go ahead and give a 95% confidence interval. Okay, with reasonable surety, I guess. So there's my my mu, my sample mean, and I just plugged that in my calculator, those 10 numbers, and got my sample mean. And then there's all that. There's the formula right there for the confidence interval. Okay, so 95% confidence interval, my z-score would be 1.960, so plug it all in, and I get that. So I'm going to add 30.4 plus this number and 30.4 minus that number, and I get my 95% confidence interval to be between 26.06 and 34.74. Okay, so now number 3 is this. It's asking, are you convinced that the mean odor threshold for the students is higher than the published threshold of 25 milliliters? Well, here's my 95% confidence interval, and since this 95% confidence interval is above the mean threshold right there, then this suggests strong evidence that the mean odor threshold for the students is higher. Okay, so because 25 is lower than the 95% confidence interval right there. All right, and then don't forget about your type 1 and type 2 errors, and there's a video on that as well. So basically, if we accidentally reject HO, if we get some statistics that say it's significant to reject HO, but when in fact HO was true, that's a type 1 error. And if we do the opposite, if HA is true and our decision is correct by rejecting HO, or we do a type 2 error is made. Okay? All right. Take care, everybody.